The second lab of Physics 2211 was called Motion of a Falling Object. The goal of this lab was to observe the predictive model of an object's y position as the object falls from rest to the floor and how that model compared to an experimental model in which you dropped an object of your choice. In my specific experiment, I dropped a small ball. In conclusion, it was seen that the computational model that I created was more precise of a prediction to the experimental model when drag force was added to the code. Newton's second law states that the net force is dependent on an object's mass and acceleration. For this experiment, the acceleration was the acceleration due to gravity. And because there is an acceleration due to gravity, the object's velocity was not constant throughout the drop in the experiment, and therefore the mass of the object did make a difference in the net force. Additionally, Newton's third law was introduced. Newton's third law states that for all forces, there is an equal and opposite reaction. In this particular lab, Newton's third law explains that with the force of gravity that acts upon the ball, the drag force also influences the object's speed and net force. In my experimental model, the drag force was much smaller than the force of gravity. Other physics terms introduced are drag force, which is another term to define air resistance, and terminal velocity, which is velocity in which the drag of an object is equal to the weight and the vertical acceleration goes to zero because this is the point in which the air resistance prevents any acceleration in the y direction. Next, the video of me dropping the ball was analyzed through Tracker. As the ball dropped, Tracker plotted the vertical distance from the start of the drop over a period of time. Then, based on the information from the experimental model that was analyzed in Tracker, the starter code was adjusted to create an accurate predictive model. From there, the computational data was completed both with and without the drag force applied. In the code, the mass was adjusted to account for the mass of the ball. In addition, the delta t was changed to 0.033, and the while statement was set to while t is less than 0.53 seconds to adjust for the time taken for the ball to hit the floor as shown through Tracker. For the equations, the acceleration due to gravity is negative 9.8. Fd is the proportionality constant times the ball's velocity squared, and the weight is the ball's mass times the gravity. Both of these terms were multiplied times a unit vector to make the code run smoothly. The net force is the sum of both the weight and drag force. For the first part of the experiment, the drag force was set as 0, while for the second set of computational data collected, the drag force was set by adjusting b so that the endpoint of the experimental model and computational model was equivalent. Lastly, I added two arrows, one to represent the drag force and another to represent the force of gravity. The data points pulled from the computational model without drag and the experimental model were overlaid on a graph, and the computational data, represented by the orange line, appeared to have a more negative slope and predict less negative values than the experimental model showed. Next, the proportionality constant was adjusted to make the final distance from the starting point equal for both the experimental and predictive model. Then this computational data with drag was overlaid with the values pulled from the experimental model. The red line represents the data points pulled from the experimental data, and the blue line shows the computational data with drag. As you can see, the values of the computational data with drag still predicted less negative values than the experimental model showed. By overlaying all three data sets, the models are very close to, but are not perfectly identical to each other. When there was a drag force, the slope of the predictive model became more similar to the slope of the experimental model. In both of the models, the graph displays a curved line in which the distance from the drop became increasingly more negative with each consecutive 0.033 seconds. The computational data without drag appears to predict slightly more negative values than the computational data with drag. The discrepancies in the data may be due to any misalignments in the video. In conclusion, I believe that due to how short of a distance the object fell, terminal velocity was not achieved during the drop. This can be seen because the object never had a constant velocity or an acceleration of 0. If the object were to have been thrown down instead of released from rest, the object would still have the same mass And because when the terminal velocity is reached, the gravitational force equals the drag force, creating a net force of 0. This means that if the mass stays constant, the terminal velocity would remain the same whether the object was dropped or thrown.